Alright, so for this video, we're going to recap on potential dividers. Just a quick recap. So let me just draw the diagram. Okay, so what do you remember about Kirchhoff's law? So let's just write down Kirchhoff's law first. So the voltage in is equal to the voltage across the resistor plus the voltage across the thermistor. Now, if you remember the thermistor graph, what happens when temperature increases? So as temperature increases, what happens to the resistance? It goes down. So as temperature increases, the resistance goes down. And if the resistance goes down, that means the voltage goes down. All right, so if the voltage goes down across the thermistor, so this is for the thermistor, as the voltage decreases, so that means that that goes down, so that is decreasing. That stays constant, so that's constant, right? So that's constant. So that means that must increase. So this is decreasing. So this must be increasing. All right, now let's draw the IV characteristic of the thermistor. Now, we know that V is equal to IR for Ohm's law. And what is R equal to? So R is equal to V over I. Now, in this case, it's I over V. So the gradient for this graph is equal to I over V. So instead of having V over I, it's I over V. So that means the gradient here is 1 over R. Now, can you see that the gradient here is increasing? So here, the gradient is increasing. So here, now if the gradient is increasing, that means that R must be decreasing. So 1 over R is increasing. So that means that R is decreasing. So as the voltage goes up, R goes down. So as voltage goes up, R goes down. Okay, so now let's talk about current and temperature. So as the current increases, so as current increases, okay, so as current increases, the temperature increases, and so that means the resistance will decrease. So it heats up. It heats up. That means the temperature goes up. So as the current increases, it heats up. The temperature increases, and then when the temperature increases, as the temperature increases, the resistance will decrease. So here is current. So as the current increases, it heats up. That means the temperature increases, and then the resistance will decrease. Alright, so now let's try to explain this more mathematically. Alright, so what is the total resistance of this circuit then? So the total resistance so the total resistance now is the resistance of this resistor plus the resistance of this thermistor. So what happens when this goes down? So as temperature increases, as temperature increases, RT will go down, and that means that will go down. Alright, so now let's work out what the current is. Now the current is I, and we know that V equals IR, so V is equal to IR, I is equal to V over I, isn't it? V over R. And we know that R is the total resistance, so that is V over R plus RT. This is total. So that is I. Now, if we're just focusing on this component here, so applying V equals IR just for this, and we know that R is RT. So across the thermistor, so now VT is equal to, because I is this, so it's V over R plus RT times by RT. So that is the equation for the voltage across the resistor. So the equation is VT is equal to VRT over R plus RT. Right, let me just work this out. Alright, we can actually simplify this, because what's the variable? What's the thing that's changing? Well, you know that V, what is this V here? The V is the voltage across the thermistor. So this V is this V in, isn't it? So this is this V in. Is that correct? Alright, so this is going to be a constant. This is a constant. V is the constant, and the only thing that's changing is this one. So this is the one that's changing. Right. So I'm going to make everything in terms of x, because now x is the variable. So this is the one that you. So this is the one that's changing, and this is the one that is what you're measuring. So let's just say that this is y is equal to. Now that's just a constant, isn't it? So I'm just going to c, and this is another constant. So c1. C2, and this is x. So C2 plus x. Okay. we can take the C1 out. So C1 is front here. Now we can separate this. So y is equal to C1, C2 plus x minus C2, C2 plus x. So this looks like the top. Sorry, we want to make the top look like the bottom. So we put C2 plus x. That, you can see that the top is the same as this. If you do C2 minus C2, that's gone, and you're just left with x. So now we can just focus on this part here. So y is equal to C1 1 minus C2 all over C2 plus x. Alright, so now we have this. Let me just write it on the left right hand side. So y C1 1 minus C2 C2 plus x. Okay, so let's draw the graph of just this spot here. So if we draw C2 all over C2 plus x, what is that equal to? Okay, so that graph looks like so what happens when x is equal to 0? So when x is equal to 0, it's C2 over C2, which is 1. So when x is equal to 0, you have 1 there. And when it's minus C2, that is the asymptote, because when that's minus C2, dividing by 0, and that's infinity. And what happens when x increases? So here, let's just say that's x, and this is y. So when x increases, the bottom goes very high, and you're just left with C2. So you're left with quite 0. So you're left with something that looks like this. Alright, so now that is just that part here, but you've got a negative. So the negative is going to look like here, because now that's minus 1. The negative is going to look like this. So now that's the negative. Now you have 1 minus the negative. So now everything is shifted up 1. So everything is shifted up 1. So instead of minus 1 there, it's going through 0, isn't it? So now it's going through 0. So now this is 1 minus C2 all over C2 plus x. And this here is minus C2. That is at the origin 0, 0. And now you're just multiplying by C1. So everything is multiplied by a factor of C1. Now this is what the graph looks like. So this is the graph of V is equal to this one here. So this is RT and this is V. So can you see what happens? So when RT goes down, when the resistance of the thermistor goes down, when it goes that way, V will also go down. And when RT goes up, the voltage also goes up. So this is the graph of this here. And that is for the voltage across the thermistor. Okay, so now let's talk about the current and the number density. Alright, so this one is Vt. Alright, so what happens when the current increases? So remember, as the current increases, So as the current increases, the temperature increases, and the resistance will therefore go down. Now, why is that? That is because the number density of charge carriers goes up. So because it's a semiconductor, the number of charge carriers, so the number of charge carriers go up. Okay, so as the current increases, the temperature increases and the resistance goes down. That is because the number of charge carriers increases. All right, now let's do a one with LDRs. All right, now what happens when the light intensity increases? So what happens when the light intensity increases? All right, so let's just draw the graph of what happens to the resistance. So this is the light intensity, and this one is resistance. So again, it goes like this, doesn't it? All right, so if the light intensity increases, what happens to R1? So R1 goes down. So when that increases, R1 goes down. And so then what happens to the voltage across there? So the voltage will go down then. So the voltage will go down. So here, R1 increases and V goes down. So when light intensity increases. If that goes down, so remember the equation, V in is equal to V across R1 plus LDR plus the voltage across the resistor. So that's constant. And this is decreasing. So the voltage across the LDR is decreasing. Hold on. If that goes up, that goes up. If the resistance goes up, yeah, so that goes, no, but that goes down. Yeah, okay. So as the resistance goes down, because light intensity increases. So when light intensity goes up, the resistance goes down, R. Let's move this up here, R. So R goes down, and therefore the voltage goes down. So that's a constant, and if that goes down, so if that decreases, then that means that must increase. So that increases. Okay, so if that, so that means that this will increase. So that means the V out will increase. So that will increase when light intensity goes up. All right, we're going to be talking about loading. So what is loading? Now loading is when you add a component in parallel to R2. So let's draw the circuit. Okay, so V loading. What is loading? Loading is when you add a component to V out, and that is parallel. All right, so what do we mean by loading? So when we are loading, we are adding a component in parallel to this. So this is R1 and this is R2. So the total resistance now here will be less. So if I draw a dotted line here, so now the total resistance is less than R2. So now the total resistance is less than R2 because the current can go in many ways. If you think about cars, because if you just have one road, but here you've got two roads, so cars can go here and cars can go here. So the resistance will be less than if you just had one R2. Okay, so that's loading. You add a component to this part here in parallel to R2. So this is loading. Now what happens when this is very high? So if, let's just say that's R3. So if R3 is very high, V out will have little effect. Because if you have a lot of resistance here, you can just forget about this and you're just left with R2. So you might as well not have that there. So if R3 is very high, V out has little effect. But if R3 is very small, then V out will be reduced. So V out will reduce. If R3 is very small resistance, then V out will reduce because now the total R is less than R2. So this is loading. Loading is when you add a component to V out. All right, what is a potentiometer? What is a potentiometer? All right, so it is a variable resistor with 3 terminals. So it's got 3 terminals. Okay, so it's got 3 terminals and it has a sliding contact. So this sliding contact can move across up and down. So it can move up and down. So the sliding contact found inside every potentiometer is a simple and cheap, and it's a compact way of producing a variable out. So what happens when it's moved towards A? So if it's moved towards A, so when that goes up, it goes through the resistor. It goes through the resistor. So if it goes through the resistor, what happens? So if you move towards A, it goes through the resistor and V out will increase. So it goes through the resistor, V out will increase. All right, now what happens when you move towards B then? So if the contact moves towards B, so if you now move towards B, what happens? If you move towards B, V out will decrease until at B it is 0. So V out until it is equal to 0 at B. Okay, so let me draw the scenarios. So when it's at A, can you see how this voltage in the voltmeter will be reading across this resistor? So now that is equal to V out at A. Well, if it's at B, so if it's at B, can you see now that voltmeter is reading across this bit here where there's no resistance? So when it's at B, it's reading at this point here. When it's at A, it's up here. At B down there, A up there. And it's not reading, so for B, it is not reading the voltmeter across the resistor, it's reading the voltage across this part here. So that's why when it's at A, it's V out, it will increase until at A is equal to V out. And that is equal to V in. V out is equal to V in. So this is V in, isn't it? From there to there, V in.
A temperature-dependent potential divider using a fixed resistor and thermistor. So as the temperature increases, then the resistance of the thermistor decreases, and this makes the voltage across it decrease. Hence, the voltage across R out, which is V out, increases. If we connect an LED or buzzer across R out, then the rise in temperature could trigger a warning. Alternatively, a fan could be triggered to cool the object in question, for example the radiator in a car. A light-sensitive potential divider using a LDR and a resistor. In the LDR circuit above, as the light levels increase, the resistance of the LDR will go down, and so the potential difference across it would increase. So let's just have a look. In the LDR circuit above, as the light levels increase, then the resistance of the LDR decreases, and so does the potential difference across it. Okay, so if you look at the top picture where it says where there's a circle and there's an R, as the light intensity increases, the resistance go down, and so the voltage across it will go down, and V out would increase because the V in is a constant. So if one of them decreases, the other one must increase. So for example, it could trigger a light sensitive alarm in a safe, for example. As before with the thermistor, if we swapped V out, so it is across the LDR, then as light levels fall, our output voltage would increase, possibly triggering a night light. Use of a rheostat to change sensitivity of potential divider. Now, if the rheostat's resistance is decreased, now this is the component at the bottom, not the circle, because the circle one is the LDR, isn't it? So it's the one with the rectangle and the arrow going through it. So if that is decreased, then more voltage will drop across the LDR, because when the resistance decreasing, the voltage will decrease across the rheostat. And you've got the two components, so the other component is the LDR, so therefore that must increase. So the LDR at a given light intensity, this increases the light intensity needed to give the same value of V out across R out. In this way, circuits can be fine-tuned to respond in the desired way. Okay, let's have a look at this question. The LDR is exposed to a reasonably high level of light intensity. The reading on a voltmeter attached across the terminals labeled V out is 10 volts. A. What is the resistance of the LDR at this intensity? Okay, so have a look at the voltage across the 1 kilo ohm resistor. That is 10 volts, isn't it? So if you look at V in is 20 volts, V out is 10. So 20 minus 10 volts is 10. So you have 10 volts and 10 volts. They both have the same voltage, so therefore they would have the same resistance. Now, what's the resistance of the second diagram, of the second picture, of the second component? So the resistance of the second component is 1 kilo ohm. So because it has the same voltage across it, it will have the same resistance, and so that is 1.0 kilo ohms. Part B. Find the reading on the meter when the LDR has a resistance of 0.7 kilo ohms. Okay, so you're focusing on the second component at the bottom. So even though the LDR has 0.7, the one at the top, we need to work out the total resistance. So the total resistance in this case is 0.7 plus 1. So if you look at the examiner's answers on the right hand side, you have R plus R out, that's the total resistance, so that's 0.7 plus 1. And because you're focusing on the reading on the meter is V out, and that is focusing on the 1 kilo ohm component. So that's why it's 1 kilo ohm at the top of the fraction. And you're multiplying by V in, and V in is 20 volts. So the answer is 11.76 volts. Okay. What is the voltage drop across the LDR at this intensity? Okay, so you know both of the voltages must add up to 20. So if the answer to BI is 11.76, you take away from 20 volts. So it's 20 minus 11.76, and that gives you 8.24 volts. C. The light intensity is altered and an increase in the value of the V out is observed. State and explain whether this represents an increase or decrease in light intensity. Okay, so there's an increase in the value of V out is observed. That would mean that the resistance has increased. Now, if the resistance has increased, that must mean that the resistance of the LDR must decrease. Now, so if you look at the examiner's answers, I've set the middle point because the voltage across the LDR must fall. So the LDR must decrease. Now, what would that have implied? So why would it go down? So it would have gone down because the resistance has gone down. And why would the resistance have gone down? That only would mean that the light intensity must increase. Because what's the graph of the light intensity graph? As the light intensity increases, the resistance of the LDR will decrease. So that's why it's the first point. Have a look at the first point. The light intensity increases. That means that the resistance decreases, and that means the voltage across the LDR must decrease. Okay, so have a look at these practice questions. A potential divider is used to detect changes in temperature using a thermistor with a resistance that varies between 1 kilo ohms or 1000 ohms and 20,000 ohms, which is 20 kilo ohms. Apart from some form of power supply, what other component is required? Suggest a reasonable resistance for it to be set to. Question 2. An LDR varies between 500 ohms and 12 kiloohms, which is 12,000 ohms, according to the level of light intensity on it. If it is used in a potential divider in conjunction with a 15-volt power supply and a 2 kiloohm fixed resistor, calculate the range of voltages that can be tapped off across the fixed resistor. 3. A variable resistor is used in a potential divider shown below. R is set at 7 kiloohms. Find the reading on a voltmeter used to measure V out. B. If the value of R is doubled, what is the reading on V out now?